Okay, so we are recording. We are technically, I guess, live, but again, I'm not expecting anyone to be here actually live right now. The only reason I'm doing this is so that we can just record something really easily. It saves me a lot of time. So what we're going to do today is go over the second right-hand rule number 2, and then we are going to talk about, I guess, the rest of the induction study guide that I had posted. I'm going to say we're going to wrap that up by Wednesday, and then I'm going to deliver a test and have you guys take that. And that will be the end of our induction unit, and then we get to move on to something called EMF, which is really neat and kind of the next natural application of this. So that's pretty cool. So that's what I wanted to do today. I wanted to go over right-hand rule number 2 and some of the questions, the remaining questions on the induction packet. And then you guys should be ready for the next step. All right, let's do it. So first of all, when we I guess last week, I had posted these slides for you guys to look at and check out. And so here they are again. We're going to pretty much ignore the force on a wire. This is typically something that we would cover if we were together, like in real life, but it's just not going to fly with how things are going on right now. It's really simple. It's not really too complex at all, but I'm trying to save time. Really what we need to be worried about is the force on a particle. So if I have a particle with charge, that would be an electron or a proton, or, for example, a mote of dust that had some electric charge on it, a static electric charge. Go way back to the beginning of this semester. We talked about how things can build up charge on them. So this doesn't have to be an electron or a proton. It could be an actual particle, a grain of sand, a drop of oil, for example, in the Millikan oil experiment, which is a famous application of this, or an actual proton or electron, but they're hard to isolate. So I don't know, you can take that for whatever it's worth. To break it down a little bit further, the really important parts of this equation, this is huge, is that there has to be a velocity for the particle. So I can't really highlight it, I guess, with the way it's kind of put in as a picture on there. But the particle must be moving. That's really important. A magnetic field does not exert a force on a stationary particle. So if the velocity is 0, the entire equation is 0. You cannot put a magnetic force on a stationary charged particle. You can put a magnetic force on a stationary magnet. Keep in mind that there's a difference between what we're talking about. We're talking about magnets that are interacting with other things that actually aren't magnets. A proton is not a magnet, nor is a single electron, nor is a grain of sand that happens to have an electric charge. So we're talking about magnetic fields affecting things that are not traditionally magnetic. And the only way that's possible is if they have electric charge and they're moving. So what we find is that the magnetic force and the electric force are strongly related to each other, and that's why all this exists. So where was I going from there? You have to have it moving. Okay, let's talk about the right-hand rule and the application of this. And by the way, don't be alarmed by the fact that this is you've got this electric force in the first term. So what they're doing is they're telling you if you wanted to calculate the total force, the total net overall force, that's on the left-hand side of the equation there, then you would have to add the magnetic force acting on the particle, that's what you know, QVB, plus the additional electric force acting on the particle. So you have to add up, remember when we talk about the net force on something, we're adding up all the possible forces on it. So that's why that equation is written that way. But what we're really going to focus on is just the magnetic force part, which is the charge multiplied by the velocity of the particle multiplied by the magnetic field. And it's a little tricky because all of these things have to be at right angles to each other. And that's where right-hand rule number 2 comes in. So I've actually thought about, do I want to go a little bit deeper into the mathematics of how this all works? it's something called a cross product. You'll notice that when they write in this equation QV times B, it's actually a x, a multiplication symbol x, not a dot. And that's not an accident, okay, right? It's actually specifically something called a cross product, which in mathematics is written with an actual multiplication symbol that's an x, whereas a dot product is different and it's written with the multiplication symbol that's just a dot that you may have seen in algebra on that. So I've thought about if I wanted to go a little deeper into what a cross product is, and I decided no for now, but if you guys are like interested in that kind of mathy stuff, we can do it. I'll tell you what, knowing how to take a cross product, if you've never heard of it or never learned it, knowing how to take a cross product of two vectors is like the first hurdle probably you'll need to overcome in college engineering or college physics. Like those mathematical hurdles of things that you don't really do that much of in high school, and then you get to college and it's like, this is like the foundation of so much engineering and physics. It's taking a cross product of two or more vectors. So if you guys are interested in that, I can do a little bit more on it. But for now, let's jump over to the study guide and talk about some of these questions that were on here. So starting with question 4, a proton, which has a charge of 1.6 times 10 to the negative 19th coulombs, enters a magnetic field and enters the specific magnetic field from question 3 at a speed of 40,000 meters per second. And what is the force that that electron feels? So I guess we would need to know the answer to question 3 in order to do that. And I'm not going to spend too long on that, but I will show you guys the explanation in just a brief moment, because I do want you to have it if you've been struggling. So we've got a solenoid, and it's going to be unwrapped and pulled into a straight wire. So it has, importantly, the most important part is really that the current through the solenoid was 2.5 amps. I'm not going to be worried about the loops or anything like that because I'm going to unwind it and pull it into a straight wire. So I'm not concerned about the length or the loops or anything like that when I pull it into a straight wire in question number 3. I want to know what is the magnetic field strength at a distance of 30 centimeters. Remember, I need to use my standard metric units, so that's 0.3 meters. And I want to know what the magnetic field is at that distance away from the wire. So with all that said, I can plug it into my equation and solve it, hopefully without too much stress. The magnetic field at some distance away from a straight current carrying wire is mu naught times the current divided by 2 pi r, where mu naught is equal to 4 pi times 10 to the negative 7th. That means I could actually rewrite that and cancel out pi if I were so inclined. So I might write this as 4 times 10 to the negative 7th multiplied by 2.5, that's the current, divided by 2 times the radius, that's 0.3. Remember, I canceled out the pi's, the pi in mu naught and the pi in the denominator there. And so if I punch those into a calculator, oh no, I don't have my calculator with me. I think I brought it upstairs. This is live, guys. This is live. You know what happens when things go live? Things go wrong when things go live. And there's scientific notation in it, so I'm not even going to be able to do it in my phone easily. So to the Google we will go, to the Google we will go. Hi-ho, the dairy-o, to the Google we will go. All right, you guys want to see how we do this? Actually, what we're going to do is we're going to go to Symbolab, because Symbolab is the best website on the internet. I don't know, that might be an exaggeration. That might be an exaggeration, I'm not sure. 4 times, or actually we're just going to do 4e. Do I do it like e? Like that's the natural number, but it's also, yeah, no, maybe a capital letter E. Yeah, that worked. Okay, so that's my 4 times 10 to the negative 7th times my 2.5, and then we're going to divide by 2 times 0.3, which is just 0.6. So let's make life easy on ourselves. And we've got 1.67 times 10 to the negative 6th. 1.67 times 10 to the negative 6th. And if I do a quick reality check on the numbers, I think that makes sense. So 1.67 times 10 to the negative 6 is our magnetic field. That would actually be in units of Tesla, T. I think one of the Khan Academies I posted talked about those units. They're strange. The units of magnetic field are really, really weird, but there you go. That's what you got. So now that we know the strength of the magnetic field, we can go forward and answer the actual question in number 4, which was, okay, what is the force that proton would feel? It's actually a 2-part question, I guess. Well, no, that's actually a typo. I don't know if anybody caught that, but I think that should be a proton in question number 4. And then in question number 6, we're going to say, okay, do the same exact picture. You don't have to redo the math, but if it were an electron. Proton and electron have the exact same charge in coulombs. The only difference is one is positive and one is negative. So we wouldn't have to do the math twice. The only thing that would change would be the direction of our answer. Okay, so the force would be the same because all the parameters would be the same, but the direction of our answer would change. I'll talk about that in a second. So let's go back to our whiteboard and set up the next part of this. We know that the magnetic field is 1.67 times 10 to the negative 6th Tesla. So I apologize for not having the camera turned towards the whiteboard. We're working on it. A one-man show over here. We know that's our magnetic field. We know that we have a proton, which has the elementary charge of 1.6 times 10 to the negative 19th. It's actually 1.67 times 10 to the negative 19th, I think. No, I don't know. No, it's 1. I can't remember. That's good enough. So that's our charge in coulombs. That's a negative 19. And then it's entering that magnetic field at a velocity of 40,000 meters per second. Quite fast, although for a proton, not really that fast. And so what is the strength of the force? So we're going to go, our force is the charge times the velocity times the magnetic field. And the reason we write it like that is that thing I was talking about earlier with the mathematics of the cross product. We are going to take the right angle, all 3 of these vectors, the force, the velocity, and the magnetic field, are going to end up at right angles to each other. Well, technically, the velocity and the magnetic field don't have to be, but the force will be at a right angle to them. And the reason we do it that way is, well, what am I talking about? Time out. It's live, unrehearsed. Velocity and the magnetic field don't have to be at right angles to each other. We'll talk about what happens if they are not. But the force is going to end up being at a right angle to both of them. So to the plane of the velocity and the magnetic field vectors, those are going to be lying in some kind of plane, whether they're at 90 degrees to each other or not. The force on the particle is going to be perpendicular to that plane, and that's what the cross product gives you. So we'll talk about what happens if the velocity and the magnetic field are not at 90 degrees to each other. But for now, let's just assume that they are for the purposes of this question. And the math is pretty straightforward because of that. You can pretty much ignore all the fancy vector math and just multiply the numbers together. So I'm going to have to go back to Symbol Lab to do this because I've got scientific notation and no calculator. 1.6 times 10 to the negative 19th and 40,000 and 1.67 times 10 to the negative 6th. I just need to multiply those three numbers together, and that will give me my force on my particle, some number of newtons. I think I'm actually going to skip it to save time because I want to talk about the next part of it, which is the direction. So question number 5 says, draw a diagram including the velocity, magnetic field, and force vectors. And we're just going to assume that they're at 90 degrees to each other. It's not stated, and there are multiple correct answers. But the trick to this is that we need to follow the right-hand rule. So this slide is giving you kind of two different interpretations of maybe like how to use the right-hand rule, but they have the same result. I like to use the one on the right-hand side of this screen, where your hand is going to get split up essentially into 3 different parts. So there's your thumb. This is going to be one vector. There's your fingers, kind of like if you were making a finger gun. That's going to be the direction of the magnetic field. And then the direction that your palm points. So with my other 2 fingers here, and this is really hard, like not in real life, but I'm making a shape with my hand that gives me 3 right angles. So my thumb and my fingers here are at a right angle to each other, making a little finger gun. And then I've got the direction that my palm would point. Right, so the direction, I just wrote on my hand, the direction that my palm would point in that case would be my 3rd direction, or my 3rd vector. So in the drawing here, they're just holding their hand like this, and they're saying, oh, okay, the direction that your palm points is the 3rd vector. And that tells you, I guess, you can use that to figure out the direction of your unknown. If you know 2 of the 3, then the 3rd, because if you hold your hand in this shape, no matter which way you rotate it around, if you hold your hand in this position and keep it locked essentially, then if you know 2, you'll always have the answer for which direction the 3rd one is pointing. It's kind of a hack, I guess, to skip the algebraic part of this and just figure out the direction using a little trick, I suppose. So I'm going to attempt to draw this example to the best of my ability. I'm going to try to use multiple colors to hopefully help me. Red never shows up very well. We're going to start with the velocity, and we're going to call that our blue vector. So let's say that the velocity starts coming in this left to right direction, like so. The easiest way to draw this is to not do 3D. The easiest way to draw this is to use what we talked about last week. When we need to show something going into the page or out of the page, we use dots and X's. So just as a quick refresher, a dot is a vector that is coming out of the page, and an X is a vector that is going into the page. Like an arrow that's flying towards your face versus an arrow that's flying away from your face. All right. So people be blowing up my phone. That's fine. Okay, so it's much easier to do that instead of attempting to actually draw in 3D. If you want to draw in 3D, that's fine, but it's much easier to actually do that like that, especially given the fact that you're doing this on Google Docs. So like, how in the world could you do this on Google Docs? I'll show you how to do a drawing on a Google Doc if you guys have never done it. It's really not that hard. We've been going for about 20 minutes, so we are going to stop somewhat soon. My second vector, I'm going to make the magnetic field. Remember, Q, this is actually not a vector. It does not have direction. And that's why when we wrote out the equation, F equals QV times B, Q doesn't get to be all by itself. It's grouped with V because it's just a scalar. It doesn't have direction. All it does is scale up or scale down the amount of force. Cool. All right, fine. So the next vector that I'll draw, though, is the magnetic field B. Let's say that the magnetic field B is going up the page from the bottom. So it's going from bottom to top. And we're going to say this is like a uniform magnetic field. So as the particle moves through the magnetic field is constant. That's really important. If the magnetic field were changing, which we'll actually talk about next unit, that's when we talk about EMF, which is amazing and awesome and one of the most important discoveries like ever. But if the magnetic field were changing on this charged particle, well, then our math would become incredibly more complex, right? But because the magnetic field is uniform, or in other words, constant, we're good to go. So the question is then, which direction will the force on the particle be? Which direction will the force on the particle be? I'm going to do that in red, I suppose. So we're going to use the right-hand rule. I'm going to put my, does it matter? No, I'm second guessing myself. It does matter. If I do V that way and B that way, then the answer would be that. But if I do B as my thumb and V as my fingers, then the answer would be that. Okay, so it does matter. So what we're always going to say then, and you have to remember this, is that your thumb is going to be in the direction of the velocity. So the thumb is going to be in the direction of the velocity of the particle, and your fingers are going to be in the direction of the magnetic field. And then the direction that your palm points in, so like for example, right now my palm is pointing up. Okay, right now my palm is pointing down. All right, so thumb always velocity, fingers always magnetic field, and the direction your palm points will tell you the direction of the force. So in this case, thumb in the direction of the velocity, fingers in the direction of the magnetic field. My palm is pointing towards you, towards the camera, so the force is actually coming out of the page at you. Weird. You have to think about this stuff in 3D. So the force will actually be coming out of the page at you in this example. That means the particle, if the particle were traveling along this direction, what would a force coming out of the page do? If the particle were traveling along in this direction, a force coming out of the page would turn it towards you. I lost the track there, right? A force coming out of the page would turn the particle in that direction. So that's pretty neat. We can cause particles to move in a circle. Well, at a certain point, actually no, with this setup it would continue to rotate and then it would come back around and rotate, and we could cause that particle to spin in a circle because of that. Well, that's pretty neat. So the next question on the study guide asks about circular motion, and it's a little bit trickier, but I guess I'm realizing that we had a little bit more time that we needed. So here's what we're going to do. I'm going to wrap this up here at this point because I've been going for a pretty good amount of time and I want you guys to not be overwhelmed in one single video. So I'm going to stop here with this. Where you should be at now, quite honestly, is let's just look back at the study guide. Remember, if it's an electron, all that happens is the direction will be reversed. All that happens is you flip the direction, just flip it around 180 degrees. So if an electron, it wouldn't be coming out of the page, it would be going into the page. The circular motion question might be kind of tricky in number 7, but I want you guys to give it a try, and on Wednesday we'll talk about it. Then as we go into 8 and the rest of it, it's really not too bad. You guys can do the rest of this pretty easily. So the only question that's kind of tough left on this will be number 7. So we'll talk about number 7 on Wednesday. I'll answer any questions that you guys have, and then from there I'll give you a quiz, get you a chance to earn some more points, keep moving forward. So stay safe, If you ever need anything, you know where to find me, and I will talk to you guys soon. Thank you for tuning in, and I hope you guys have a great day.